Here in this article, we are going to learn the comparison between Young's double slit interference pattern and a single slit diffraction pattern. Already we have studied these two experiments. This is not only, it is also a differentiation between interference and diffraction. Interference we have learned, diffraction we have learned, and the difference between them we want to summarize in this chart. These questions that can be asked like this also. Distinguish between interference and diffraction. Also it can be asked, distinguish between Young's double slit interference pattern and single slit diffraction pattern. So to answer this, we are having this total chart, and in the chart some of the quantities are mentioned which can give the distinguishing properties as well as comparison between different things. So let us start. Here this is physical quantity, Young's double slit interference pattern, single slit diffraction pattern. Now the first quantity which is to be measured over here, or which is to be considered, that is a fringe width. Manuel, one thing I would like to tell you, when the Young's double slit experiment it is performed, that time the slit width we used in this, it is very small. It is a few millimeter, and about 30 to 40 bright and dark fringes can be obtained. When a single slit diffraction pattern is used, in this the slit is of about 1 millimeter width and near about 20 to 30 fringes, that is the maximum and minimum, or minimum and maximum intensity are observed around the central bright point. Now here we are going to summarize for fringe width. The width for Young's double slit interference pattern, it is W equal to lambda d upon small d. What is it? It is the fringe width. We have obtained this expression. Also, the fringe width for single slit diffraction pattern, it is W equal to lambda d upon A. But this is except for central bright fringe. In a central bright fringe, the width is maximum. The width is maximum, and for all other it is near or equal, and that's why especially we have written here except central bright fringe. Now for nth bright fringes, we have seen that in Young's double slit experiment the central bright point is formed, and on both sides of the central bright point there are dark bright points, or dark bright fringes, or dark bright bands are formed on both sides of the central bright point. Also here in this single slit diffraction, the alternately the bright and dark, or we can say that the points of maximum and minimum, or minimum and maximum, are formed on both sides of the central bright point. Of course, we are going to learn the nature afterwards. First of all, let us see some of the comparisons for certain physical quantities. First is the phase difference delta between extreme rays. If we consider the extreme rays, then the phase difference between them, it is n into 2 pi. N is integer. N is integer. Here it is n plus half into 2 pi or n minus half into 2 pi. We have seen that when the interference pattern is going to form, that time there is a integral multiple of wavelength, there is a path difference is integral multiple of wavelength and odd integral multiple of wavelength. Phase difference is integral multiple of 2 pi and odd integral multiple of 2 pi, and that can be obtained. See here, this n plus 1 by 2, n minus 1 by 2, these two factors that represents the odd integer. It represents the odd integer. Next, for this central point, we are written except central bright or except central bright means n equal to 0. It is not possible in this case. Here it is n equal to 0, 1, 2, 3, 4 like this. It is integers starting from 0, but here the value of n it is 1, 2, 3, 4, 5, 6 like this. Now angular position theta. For Young's double slit experiment, it is n lambda upon small d, where small d it is the distance between two currents, two sources or two current sources. Here it is n plus 1 by 2 into lambda upon A. A is slit width, or n minus 1 by 2 lambda upon A. A is the slit width, lambda is the wavelength. Path difference delta x between extreme rays. When we consider the extreme rays, that time the path difference delta x between extreme rays, it is n lambda. It is nothing but n plus half into lambda. Again here n plus half, it indicates the odd integer. Distance from central brightest spot. The distance of nth central brightest distance of bright spot or bright band, bright fringe from this central bright band, it is n into lambda d upon small d. That is nothing but n into w, where w is the width. W is the width. Next, here it is n plus half into lambda d upon small d, which is equal to n plus n minus half. It should be n minus half into w. For nth dark fringes, we have said alternately the dark and bright fringes, they are being formed on both sides of the central bright point, and therefore for nth dark fringe, phase difference delta between extreme rays, it is n minus half into 2 pi or n plus half into 2 pi. And for single slit diffraction pattern, it is n into 2 pi. Now here you will find that these conditions, they are interchanged. They are interchanged. For interference pattern, for dark point, what are the conditions? It is for bright point for the diffraction pattern or for maximum point. Angular position theta, n minus half into lambda upon d or n plus half into lambda upon d, it is n lambda upon A. A is slit width, d is distance between two coherent sources. PD delta x, that is path difference delta x between extreme rays, n minus half into lambda or n plus half into lambda, that is equal to n lambda. Here distance from central bright spot, it is n minus half lambda d upon small d into equal to nw, w is the weight, or n plus half into lambda d upon small d, that is nw, w it is weight. Now in this case, this w it is given by lambda d upon small d, and here in this case it is given by lambda into capital D upon small a. The difference between the intensities, look at here, the intensity for all the bright bands it is same, also the intensity for all the dark bands it is same. But here this intensity it is going to increase. Mind well, at the central bright point, this intensity it is maximum. It goes on decreasing on both sides up to the first minimum. Here, these are the points of the first minimum. This is central bright point, or it is also called as a central maximum. Intensity is going to decrease for next. Here the intensity is maximum of all the peaks. Here the intensity goes on decreasing. Further it will have a less intensity. Further it will have a less intensity on both sides. One thing please be noted. Here the width of bright band and dark band it is same, and that's why we have proved one derivation. The width, that is dark bands or bright bands, they are equispaced. But here the width goes on changing. Intensity goes on changing, the width also goes on changing. Next, here in this case, the distance between slit and the screen it is too much maximum, or we can say that D is very much greater than capital D is very much greater than small d. D is the distance between the slit and the screen. Here capital D is very much greater than E. And this way we can put some comparative statements, comparative informations regarding these Young's double slit interference pattern and single slit diffraction pattern. We are interested in finding the distance of nth dark point and nth bright point. Let y and d distance of nth dark point. Now from figure, we write this theta n equal to or theta n d for dark point. The angular separation of nth dark point it is equal to y n d upon capital D. Look at this. This is the y distance. Now suppose that this point P, it is a yn distance away from P0 point. Then, and this lens it is kept close to the slit, and therefore we write opposite side divided by adjacent side, that is equal to theta, tan of theta, opposite side divided by adjacent side. Tan theta nd equal to y&d upon capital D. Now, theta, as theta is very small, this tan theta nd equal to theta nd, that is equal to y&d upon D. This is suppose equation number 1. Or this I'll write equation as A. Also, for first minimum, we are having this condition theta equal to n lambda upon A. We have theta nd equal to n lambda upon A. And therefore, this is equation suppose B. From A and B, we write y and d upon capital D equal to n lambda upon A, and therefore we write this y and d equal to n lambda into capital D upon A, which is equal to n into W. W is weight. W is weight. And Y BD or YNB, it is a bright point. Distance of bright point or nth bright. And therefore from figure we write for bright point we are having, or maximum point we are having this condition theta and B equal to plus or minus n plus half into lambda. This is suppose equation C. From equation A and C, we write, from this equation A and C, we write y and B equal to y and B equal to n lambda n plus half into lambda d upon small a, which is equal to n plus half into W, where this W is width of the, this W it is width of the central bright point and first minimum, central bright point and first maximum. From this we write width it is equal to width of central bright that is equal to 2W, that is nothing but 2 lambda d upon A. 2 lambda d upon A. Got this? So this way we can find the expression for central bright point. Mind well, here this point it is first minimum, this point it will be first minimum, and the distance between these 2 points, that is the width of central bright point. Width of central bright point. It means what? The central bright point, it will be spread between 2 first minimum. Between 2 first minimum.